Question 1 on the final exam review. Evaluate this expression. So what you have to be able to read here is that the top number is the power and the bottom number is the root. So instead of writing it as 4 to the 5 over 2 power, I'm going to want to write the square root of 4, because 2 is the root, so it's a square root, and then that to the 5th power. The denominator of an exponent is the same as your root. So now the square root of 4 is 2. So this is 2 to the 5th power, which is 2 times 2 times 2 times 2 times 2. So that's 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Similar explanation to number 1 is that the root number is the denominator when I write an exponent. So basically I turn the exponent into a fraction, the power over the root. So it's like backwards of our first step from number 1. That's all there is to do with this one, is just rewrite it in its equivalent rational exponent form. This is root form, radical form, and this is rational exponent form. Questions 3, 4, and 5 is to simplify exponential expressions. So the first thing we're going to want to look for is applying any outside exponents. Apply outside exponents. And when we do this, we multiply the exponents by all the ones on the inside. So this has an exponent of 2, and I'm applying an exponent of 5. So it becomes 2 times 5, or x to the 10th power. Neither of these other two problems make us do that. But the next thing I would typically do in problems like this is move any negative exponents. Because our negative exponent property lets us turn something into a positive exponent by switching the side of the fraction bar it's on. So if I look at a problem like number 4, this w to the negative 2 has to come down. This w to the negative 4 has to go up, and the z to the negative 3 also has to go up. All right, but the 12 and the 15, those are not part of the w's. They're coefficients, but when we're working with exponent properties, they have their own exponent. They each have an exponent of 1. All right, so they don't move with the w's. They're not actually part of the w's. Then over here, maybe I do something like that. All right, there's another way to handle number 5, but we'll try and stay consistent. So number 4 comes out to 12 w to the 4th power, z cubed, and then z cubed again, over 15 w squared. And number 5 comes out to p cubed times p to the 6 over p to the 9. So now everything has positive exponents. Now I'm going to work on combining like bases. So if I look at number 4, I have w's and z's, and I only want one of each, so I got to combine them. The z's are easy because they're on the same side. They work together. I have 3 z's multiplied, 3 z's multiplied. That's a total of 6 z's multiplied. All right, but with the w's, it's slightly different. They're on opposite sides. They work against each other. The top side has 4, the bottom side has 2. They kind of butt heads until one of them runs out. So the bottom w runs out, the top w has 2 left. If you remember in class, I kind of wrote it out like w, 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 w over w, w, 4 on top, 2 on bottom. I cross out until one of them runs out. There's 2 left on top. So you can kind of think of it, they work against each other, which side wins. So there are 2 w's left on top. The 6 z's from the z's working together, and then 15 on bottom. There's one more step I'm going to do here that isn't so much about simplifying exponents, but I'm still going to do it just because it's technically the best way to get our answer. The last problem over here, the p cubed and the p to the 6 make p to the 9 over p to the 9. Well, if they fight and they both run out, I end up with p to the 0 or just 1. 1 is my best answer for this problem. I end up with everything canceling out, and this is the 0 exponent property. So if you ever get to a point where you see an exponent of 0, that piece can just become a 1, which is almost like it cancels out. The last thing I want to do with the fraction is I'm going to simplify numbers if I can. So, if you have like 2 squared, you can turn it into 4, or if you have a fraction like this, both of these are divisible by 3. 12 over 15 is the same as 4 over 5. So I can simplify the number parts just like a normal fraction and just leave the variables alone. Write that a little better. 4 over 5. All right, so this is kind of like a little checklist. The one extra thing I didn't add here is that sometimes you get to cancel out a 0 exponent. And as soon as you see one, you can do this. It doesn't have to be in any particular order. So these aren't terribly long problems as long as you keep this checklist in mind. All right, all the individual steps are pretty easy. There's not a lot of calculating to do. We just have to remember what the steps mean. And, we shouldn't end up with duplicates of any w's or z's or any letters. And we shouldn't end up with negative exponents. So as long as those two things are accomplished and you didn't do anything illegal, you should be good. A couple more exponent-based problems. Back in the lesson, we talked about how if I have two numbers that are the same and their exponents also match, then the equation works. So it's kind of our goal here is to get common bases. So here, I just want to point out that the 9 has an exponent of 1. Anything you don't see an exponent for, you can just imagine there's a 1 there. So when I don't have matching bases, what I have to do is my factor tree. My goal is to find something that matches all the way across the board. So technically I could do 3 to the 4th power and 3 squared, but just working with 9s is easier. 81 splits into 2 9s, so 81 is the same as 9 squared. And this is our way of getting common bases, is just do a factor tree and find something that matches. So now I have to apply the outside exponent. I do that by basically distributing 2 times 2b minus 3, 4b minus 6. And now I just care about the exponents. The bases match, now I need to get the exponents to match. So I need to find something for b that makes this situation match. So now I just solve like a normal equation. 4b equals 7. One last step, divide by 4, and I get b equals 7 over 4, or 1.75. If I were to plug that back in, 1.75, that's 3.5. 3.5 minus 3 is 0.5. Basically, it comes out to the square root of 81 equals 9, which is true. So these ones are sometimes a little hard to plug back in, but the concept here is that I need the bases and the exponents to match. Number 7 is one more little step more difficult because 125 can't just split into 25. So I actually have to go and do a factor tree for both problems. 125 is 5 cubed, and 25 is 5 squared, so they both have to get modified like this. It's the only difference between the last problem and this problem. So now I'm going to multiply by the outside exponent. I get 3x minus 9 equals 12. Add 9, 3x equals 21. Divide by 3, x equals 7. So we didn't spend a ton of time on this during the semester, but basically once you figure out the common bases, it's just a normal equation to solve. Once I get bases that match, it's just solve for the variable. So that part hopefully isn't too hard. The thing you really need to try and remember is to make the factor tree to get common bases. Problem 8 takes up a whole page on its own, but that's because we're asked to do a lot with it. First question is it growth or decay? Well, we got to look at our equation specifically right here. What's our pattern? If we're multiplying by something bigger than 1, then we're getting bigger. If we're multiplying by something smaller than 1, like this fraction here, we're getting smaller. Getting smaller is decay. So we have to look at our multiplying pattern to see which one we should be using. From there, we just have to pick out our A value and our B value. Our A value is the start number, and our B value is the pattern, the multiplier. So the start number should go in the middle of our table. So when x equals 0, y is the start number. Then I'm going to go back 2 spots and forward 2 spots. So when I go forward, I follow my pattern, times a half. Half of 4 is 2. Half of 2 is 1. Then to go backwards, I do the opposite. I divide by a half, which is the same as multiplying by 2. So 8, 16. All right, the pattern should make sense all the way down. So half of 16 is 8, half of 8 is 4. So it's a way to check your work here. So negative 216 is going to be a little ways off the graph, way up here. Negative 1, 8. 0, 4, 1, 2, 3, 4. That's our y-intercept. 1, 2, and 2, 1. And we get this nice exponential curve that we should have gotten used to seeing during the unit. It's not like a parabola where it goes back up. It just one side is steep, the other side flattens out. All right. So domain for these, if you remember, we're allowed to plug anything in for x. There's no rules there. So we have all reals, all real numbers. And then range, because our a value is positive, we started positive, our graph is always above the x-axis. So we're going to have y is greater than 0. All right. If a is a negative value, this is going to be y less than 0 because our graph is going to be on the opposite side. It's going to be on the bottom, all negative numbers. Number 9 is an exponential growth or decay formula. First thing we're supposed to do is write a model. This follows the rough pattern of a times b to the x, but instead of b, we actually wrote this out as 1 plus r or 1 minus r, depending on if it's growth or decay. Now ours says increase, so we're going to go with growth. So we're going to use this one. All right, so we're going to fill in the 1 plus r formula. So r is the rate, and 1,000 is the starting point, or the a value. All right, but we don't use the number 10. We actually need to turn that into a decimal. So 10% equals 0.1. I move the decimal 2 places, so it's 0.10, but 0.1 is the same thing as 0.10. So my y equals a, 1 plus r. A is $1,000. That's where I start, just like the graph on the last one. The a value is a start point. And then 1 plus 0.1 to the t. We usually use t instead of x because we're specifically talking about time here. So instead of 1 plus 0.1, 1 plus 0.1 is 1.1, so we can just write that in there. So that's our model. Remember, it roughly fits 1 plus r to the t. Sometimes it'll be minus if it says decreases. And we're supposed to find the value after 5 years. So we can either multiply by 1.1 5 times, or put this right in a calculator with an exponent of 5. They'll both get us to the same point. So these vintage cards should be worth $1,610.51. So quite a big increase for 5 years. 10% is a big growth. Number 10 has us finding a couple of patterns. So just a little bit of vocab review. Arithmetic is an adding pattern. Geometric is a multiplying pattern. So our goal is to look and see if we have a consistent pattern. To get from 2 to -4, we can either do times -2 or -6, but -6 doesn't make sense if we look at the next number. So if I do times -2, -4 times -2 is 8. 8 times -2 is -16, so the pattern follows all the way through. Because it was a multiplying pattern, this one's geometric. And our next three terms are going to be -16 times -2 is +32, times -2 is -64, times -2 is +128. Letter B, I'm either dividing by -1/4, or times -1/4, sorry, divide by -4, or I'm subtracting 5. But if I look at the next step, multiplying by a fraction doesn't make sense, so we'll try -5. -1 minus 5 is -6. -6 minus 5 is -11, so it looks like we found a pattern. All right, this is an adding or a subtracting pattern, so it's arithmetic. And then we'll keep going and find the next three terms. -16, and then -5 is -21, and -5 one more time is -26. So these ones should be easy. It's more or less, do you remember what the vocabulary means? If I ask you to look for the pattern, we're pretty good at that. We just need to remember what the vocabulary means.